of our AP Calculus AB review, where we focus on differentiation and differentiability. Again, recall the significance of a derivative. A derivative is essentially the central concept of calculus. The idea is that if we applied the slope of a secant line over an interval, aka the average rate of change, between an interval x plus h and x, if we take the limit as h goes to 0, then we're going to end up with a tangent line, which provides us not with the average rate of change, but the instantaneous rate of change at a specific point, since a tangent line touches at specifically one point. So instead of delta y over delta x, we have dy over dx. An equivalent definition is as x approaches a. Again, this is the average rate of change as x approaches a specific value a, which becomes the limit as x gets closer to a tangent line. So the derivative is defined as the limit of the slope of the secant line as h goes to 0 or as x goes to a, the point of interest. It represents the following: the slope of a tangent line to the curve at x equals a, the instantaneous rate change at a point x equals a. It's different from the average rate of change, as average rate of change is defined as the rate of change over an interval, while the derivative defines a change at a single point in time or a single point on the x-axis, hence why we call it the instantaneous rate of change, because it measures rate of change at a specific instant. Ooh, did not notice that there. So, estimating derivatives and basic rules. If provided a table of values, the derivative of x equals a can be estimated by calculating the average rate of change between the two data points closest to x equals a. If provided a graph, the derivative can be calculated by drawing a tangent line to the graph at x equals a and estimating the slope of the line. If it's just a line segment, then your derivative at the point is just a derivative of the line segment containing the point. Provide a function f, the following function rules apply. Constant rule. If f of x equals c, then f prime of x equals 0. Again, that's the idea, is that derivative measures rate of change at a point with a constant function. There is no change because we're, well, constant. A constant multiple rule. If g of x equals c times f of x, then we can factor out the c, and the derivative of g is just equal to c times the derivative of f. And lastly, we get to the power rule. Actually, we might have a couple more rules. Yes, we do. If f of x equals x to the nth power, then the derivative is n times x to the n minus 1 power. The product rule, if h of x equals g f of x times g of x, then the derivative of h is equal to the derivative of x times g plus f times the derivative of g. And lastly, we have the quotient rule, where if h of x equals g of x divided by, f of x divided by g, the derivative of h is equal to derivative of f times g minus f times the derivative of g all over g squared. And then recall that we will encounter a vertical tangent line wherever g of x is equal to 0. Key derivatives to know, again, this is from our table right here. So we have our trig: derivative sine equals cosine, or derivative of sine is cosine, derivative of cosine is negative sine, derivative of tangent is secant squared, derivative of cotangent is negative cosecant squared, derivative of secant is secant x times tangent x, and derivative of cosecant is negative cosecant times cotangent. Ooh, that's a lot to say. And then you get to the really difficult derivative, e to the x. E to the x is so difficult to memorize, it is literally itself. Derivative of a to the x is similar. It's a to the x times natural logarithm of a, which reduces down to e to the x when a equals a, because the natural logarithm of e is just 1. The derivative of natural logarithm of x is always 1 over x, and then the derivative of log base a is 1 over x times natural logarithm of a. And then lastly, we have our derivatives of our inverse trig functions. Again, when you see this negative 1 right here, it doesn't mean it's signed to negative first power or whatever trig function negative first power. It's telling you it's an inverse trig function. I'm not going to say all of that there. You can pause and look over and make sure, okay, you have it right in your notes if need be, because I am winded from saying derivatives at this point. So as an example of derivative rules in effect, here. If we have f of x equals x squared times the natural logarithm of x, we can see that we're going to need to apply the product rule first, working our way from outside in, because we have two functions multiplying each other, x squared times natural logarithm of x. So we apply the product rule, derivative of x squared times natural logarithm of x, plus x squared times the derivative of natural logarithm of x. So as a result, we get 2x times natural logarithm of x plus x squared times 1 over x, which gives us 2x times natural logarithm of x plus x, which leads us to factor out an x to get x times 2 natural logarithm of x plus 1. Differentiability. A function is called differentiable at a point x equals a if the derivative of f prime exists at that point. Remember that to be differentiable at a point is not equivalent to continuity. It's a little bit more subtle and we have to dig a little bit deeper. So the function must be continuous at the point. The left-sided derivative must equal the right-sided derivative at the point. So as a result, the big condition we check for differentiability is we take the derivative and we see if the derivative from the left-handed side is equal to the derivative from the right-handed side, aka are the slope of the tangent line as x approaches a from the left equal to the slope of the tangent line as x approaches a from the right. So as a result, we can see that if a function is differentiable at a point, it's automatically continuous. But if a function is continuous at a point, it is not necessarily differentiable. It must be a second point. So again, the idea here is if a problem asks you, is a function differentiable at a point, continuous but not differentiable, or neither at the point, the idea is you first want to check this condition right here, because if this condition is met, your function will be differentiable and hence automatically continuous. While if this condition is not met, you'll want to go back and check if the function is continuous. Excuse me. As an example, we can see that we're continuous but not differentiable at x equals -2 because we can see that as we approach -2, we're about I'm thinking all wrong here. If we approach x equals -2, we're going to see we get a vertical tangent line, which we can't measure, so we're not differentiable at x equals -2, but we are continuous because the limit of our function does exist. We approach the same y value, and we have our function value actually existing at that point. And then we can see at x equals 1.5 approximately and x equals 4, and that's because we can see that the limit of our derivative as x approaches a from the left does not equal the limit of our derivative as x approaches a from the right, aka our tangent line from the left side is not equal to tangent line from the right side for both x equals 1.5 and x equals 1.4. We can see that at x equals 4 we're going to get a positive infinite limit, and then at x equals 1.5 from the right-hand side, we're going to get a negative infinite limit. We're not continuous and hence not differentiable at x equals 0. We have a jump discontinuity. And x equals 2.5 because we have a removable discontinuity here. We're differentiable at all points in between, which is just this interval right here, which is kind of complicated to state, so I'll let y'all figure it out. The chain rule in derivatives and inverses. If f of x has an inner function g of x, i.e. f of x equals f of g of x, then the derivative of f can be found by obtaining the derivative of f with respect to g and multiplying it by the derivative of g with respect to x. In Leibniz notation, we say that derivative of f with respect to x is equal to df over du times du over dx, where u is equal to g of x. And in Lagrange notation, that's equivalent to f prime of x equals f prime of g of x times g prime of x. From the chain rule, the formula for the derivative of the inverse of a function f -1, I say that instead of f to -1 because f to -1 implies that it's to a certain power, at a point AB is equivalent to the reciprocal of the derivative of f at x equals a. Okay? From this, we conclude that a function is not invertible at x equals a if f prime of a equals 0, aka we have division by 0. The inverse function theorem. One thing to be careful with here is that this is x equals a referring to the original function f. If it asks you for the derivative of the inverse at x equals a specific value, that refers to the x value of the inverse, which is the corresponding y value for the original function. So hence, in order to solve for the x value of the original function, you set your function equal to the y value and solve for the specific x value at which your function is equal to the y value. When dealing with a function that contains products, quotients, and inner functions, it's best to work from the outside inwards. Okay, so if we look at 2x plus 3 times 4x plus 5 squared. We can see that we do have a chain rule here because we have 4x plus 5 squared. But first off, before we get to chain rule, we can see working our way from the outside in, we have a product rule of two functions multiplying each other. So the first rule we're going to apply is a product rule. We have the derivative of 2x plus 3 times 4x plus 5 squared plus 2x plus 3 times the derivative of 4x plus 5 squared. Okay? So as a result, we take the derivative of 2x plus 3, which gives us just 2, times 4x plus 5 squared. And then we have 2x plus 3 times the derivative of 4x plus 5 squared. Okay, so we take the derivative of 4x plus 5 squared with respect to 4x plus 5. So 4x plus 5 is our u here. So that's going to be 2 times 4x plus 5. And then we take the derivative of our inner function, which again, u is equal to 4x plus 5. The derivative of that would be just 4. So as a result, we get from simplifying 2 times 4x plus 5 squared times 8 times 2x plus 3 times 4x plus 5. Simplifying that result down gives you 2 times 12x plus 17 times 4x plus 5. Lastly, we get to implicit differentiation. For equations that cannot be solved explicitly for y, the chain rule can be applied to find the derivative dy over dx. We differentiate both sides of the equation. We group all terms containing dy over dx to contain one side, and all terms to the other side, and then we solve subsequently for dy over dx. As an example, if we have x squared plus xy minus y squared equals 1, okay, we take the derivative of both sides, which gives us 2x right here, and then 2x is the derivative of x squared, and then for x times y, we have to apply the product rule. So derivative of x times y, which is just going to be 1 times y, plus x times the derivative of y, which we label just dy over dx. Lastly, we take the derivative of y squared, which is negative 2y, and then because y itself is an inner function, we multiply that by dy over dx. Next, on the right-hand side, we have that the derivative of 1 is just 0 because 1's a constant. So now we group together all of our terms to one side and all of our terms containing dy over dx to the other side. So as a result, we're going to get, we move 2y dy over dx to the right-hand side, and then we move x times dy over dx to the right-hand side, and we're left with 2x plus y on the left-hand side. Factoring out the dy over dx, we get dy over dx times 2y minus x, and we divide both sides by 2y minus x in order to get our dy over dx, hence subsequently giving us our derivative for the implicit function. For implicit differentiation and slopes of tangent lines, when asked to find the x and y coordinates such as the slope has a specified point, whether it's a specific numeric value or it's 0 or a vertical tangent line, we use the value of the derivative and the original equation to set up a system of equations. We solve the value of the derivative for x or y and plug this result into the original equation to eliminate a variable and solve the remaining variable. We then use the solution of one variable to solve for the other variable from that system of equations. Okay? If a problem asks you, is it possible, you still follow this line of, is it possible that such a slope is possible, y equals dy over dx equals 0 or vertical tangent line. Again, you follow these steps, and then what you look for is to see whether the equation of the curve is satisfied or you end up with an imaginary answer. In such cases, if we end up with an imaginary answer, it's not possible since we work strictly with real numbers in calculus. And this completes day 2 of the AP Calculus AB review.